In this video, we're going to investigate the velocity and the acceleration of a particle that is moving in a circle. So, let's suppose that we've got a particle P of mass m which is moving around a circle of radius r and centre of the origin. We're going to suppose that initially the particle is on the x-axis at the point A with coordinates r0, and that at time t the angle AOP is theta radians. Now this means that the position of the particle at time t is going to be r cos theta, r sin theta, which means that the displacement of the particle P from the origin at time t is going to be the vector r, little r, where little r is r cos theta in the x direction, r sin theta in the y direction. Now to begin with, we're going to assume that theta is increasing at a steady rate of omega radians per second. Omega is called the angular velocity of P. Now if this is the case, then the angle theta at time t is simply going to be given by theta equals omega t. That's really just the same thing as saying that if you've got a car moving with steady speed s, then the distance travelled in time t is given by distance equals speed times time. So we've got theta equals omega t, which now means that we can say that the displacement, little r, is given by r cos omega t, r sin omega t. Now, given that this is the case, we can find the velocity of P by differentiating the displacement, because we know that velocity is rate of change of displacement. So we've got V equals dr by dt. Now the x component of r was the radius times by cos omega t. The radius is constant, and we know that the derivative of cos omega t is minus omega sin omega t. So the x component of the velocity is going to be minus omega r sin omega t. Similarly, the y component of the displacement is the radius times sin omega t. We know the radius is constant. We know that the derivative of sin omega t is omega cos omega t, so the y component of the velocity must be omega r cos omega t. Now we can make one or two deductions from this relationship. First thing we can do is if we take the scalar product of the velocity with the displacement, then we've got minus omega r sin omega t, omega r cos omega t, scalar product with r cos omega t, r sin omega t, which gives me minus omega squared r sin omega t cos omega t plus omega squared r sin omega t cos omega t, and of course those two terms cancel out to give me 0. And we know that if two vectors have a 0 scalar product, then the vectors are perpendicular to each other, which means that the velocity is perpendicular to the radius. In other words, the velocity is in the direction of the tangent to the circle. We can also work out the magnitude of the velocity. In other words, we can work out the speed. So the speed is the magnitude of the velocity, which is the magnitude of the vector minus omega r sin omega t omega r cos omega t, and that is simply the square root of minus omega r sine omega t all squared plus omega r cos omega t all squared. So we've got the square root of omega squared r squared sine squared omega t plus omega squared r squared cos squared omega t. And that very quickly simplifies to give just omega times r. Now, if we differentiate the velocity with respect to time, then we obtain the acceleration. So we know the velocity is given by minus omega r sine omega t, omega r cos omega t. So differentiating that is going to give me the acceleration is equal to dv by dt. The derivative of minus omega r sine omega t is just going to be minus omega squared r cos omega t. The derivative of omega r cos omega t is just going to give me minus omega squared r sine omega t. And if we pull out a factor of minus omega squared r, then we can see that the acceleration is simply minus omega squared times by little r. And little r, remember, was the displacement of p. So we've got the acceleration is minus omega squared times by the displacement of p. And this tells us two really important things. First of all, it tells me that the magnitude of the acceleration is the magnitude of the vector minus omega squared times little r. Dealing with the magnitudes, we can neglect the minus sign. So the acceleration has got magnitude omega squared times by the magnitude of the vector little r. Little r is the displacement of p from the origin, and the displacement of p from the origin has got magnitude equal to the radius of the circle. So we've got the acceleration has got magnitude omega squared times by capital R, the radius. The minus sign in this equation, the minus sign in the equation acceleration equals minus omega squared times the displacement, tells me that the acceleration is in the opposite direction to the displacement. So that means that the acceleration is in the direction towards O from P. So it's directed towards the centre of the circle. So, putting our results together, if we have circular motion where the angle is increasing at a steady rate of omega radians per second, so there is a constant angular velocity, then we have the velocity is tangential to the circle, and the size of the velocity, the speed, is equal to r times omega. And we have an acceleration acting towards the centre of the circle, whose magnitude is omega squared times by the radius of the circle. Now we can make one final observation before proceeding. We know that the acceleration has magnitude omega squared r. We know that v is equal to omega r. So omega is the same thing as v divided by r. So the acceleration can be written as v squared over r times by r. In other words, the acceleration is the speed squared divided by the radius. So we've got two expressions for the acceleration. It's either angular velocity squared times the radius, or it's the speed squared divided by the radius. Now let's move to the case where theta is not increasing at a steady rate. So we haven't got a constant angular velocity. Now, if that's the case, then we're going to have to do some implicit differentiation to find the velocity. So we've got the velocity is dr by dt, and if we do some implicit differentiation now, on the x component I want to find the derivative with respect to t of r cos theta, and that is going to give me minus r sine theta d theta by dt. Similarly, for the y component, I need to differentiate r sine theta with respect to t, and to do that I'm going to get r cos theta times by d theta by dt. Now, in very much the same way as we did before, we can take the scalar product of the velocity with the displacement vector, and that turns out to be 0, which again tells me that the velocity vector and the displacement vector are perpendicular to each other, so the velocity vector is tangential to the circle. The speed v is the magnitude of the velocity, so that is the square root of minus r d theta by dt sine theta all squared plus r d theta by dt cos theta all squared. And if we simplify that, that's the square root of r squared d theta by dt squared sine squared theta plus r squared d theta by dt squared cos squared theta. We know sine squared theta plus cos squared theta is 1, so we've got simply the square root of r squared d theta by dt squared times by sine squared theta plus cos squared theta, which is 1, so we've got the square root of r squared d theta by dt squared, which is simply r d theta by dt. So the speed v at any instant is equal to the radius times by d theta by dt, and d theta by dt is the angular velocity at that particular instant. So that's very much the same formula as we had before, which was v equals r omega. Of course, in this case, omega is not constant. So there we are, we've got our velocity v is tangential to the circle, and the size of the velocity is d theta by dt. Now, if we want to find the acceleration in this case, there is a heuristic argument that we can put together for this, which goes along the following lines. We can say we've got circular motion, so there must be a component of the acceleration of size v squared over r towards the centre. And we know that v is the same thing as r times d theta by dt, so v squared over r is the same thing as r squared d theta by dt squared, all divided by r. In other words, it's just the same thing as r d theta by dt squared. So there's this acceleration towards the centre of size r d theta by dt squared, or v squared over r. And because the speed is changing as we go around the circle, it suggests that there ought to be a tangential acceleration of magnitude dv by dt, where v stands for the speed. Now, proving these results rigorously, rather than doing what we've done so far, which is really just rather a hand wave at it, requires quite a bit of implicit differentiation and product rule work. We'll find this on the next slide, but at this stage, If you feel that you've had enough, it can be omitted. You certainly need to know and remember that the acceleration towards the centre is always v squared over r, or r times d theta by dt squared. It's useful to know about the tangential acceleration. However, the WJEC specification for Unit 3 does not require this knowledge. So let's now just try quickly to see the rigorous proof of this. So we've already established that v, that is the velocity, is minus r d theta by dt sine theta, r d theta by dt cos theta. So if we want to find the acceleration, we need to find dv by dt. Now, to differentiate the x component of the velocity, we've got to differentiate minus r d theta by dt sine theta. And we've got a product there. So first of all, we'll differentiate the minus r d theta by dt part, and that gives me minus r d2 theta dt squared, and leave the sine theta alone. Then we must leave the minus r d theta by dt part alone, and we need to differentiate sine theta with respect to t. And the derivative of sine theta with respect to t we need to do implicitly, and we obtain cos theta d theta by dt. So the second part of our product rule is going to read as minus r d theta by dt times by times by cos theta d theta by dt. So we end up with minus r times by d theta by dt squared cos theta. And again, with the y component of the velocity, we've got to differentiate that with respect to t. So that's going to require the product rule. First of all, we differentiate r d theta by dt, and that's going to give me r d2 theta dt squared. So the first part of our product rule is going to be r d2 theta dt squared times by cos theta. Then we must differentiate the cos theta part and leave the r d theta by dt part alone. So we're going to have plus r d theta by dt times by the derivative of cos theta with respect to time, which has got to be done implicitly and gives me minus sine theta d theta by dt. So the second part of the product rule on this is going to give me r d theta by dt times by minus sine theta d theta by dt. So we've got minus r d theta by dt squared times by sine theta. Now if we look carefully at this and split the acceleration into two parts, we can rewrite the acceleration as r d2 theta dt squared times by minus sine theta cos theta plus r d theta by dt squared times by minus cos theta minus sine theta. Now if we look at the first part of this expression first of all, then the vector minus sine theta cos theta has magnitude square root of minus sine theta all squared plus cos theta all squared, which in other words is the square root of sine squared theta plus cos squared theta, which is simply 1. So the left hand part has got a magnitude of r times d2 theta dt squared, and it is in a direction which is the same as the direction of the velocity, i.e. it's tangential. And we can show this on our diagram as a tangential component of the acceleration of size r times by d2 theta dt squared. We know that r times d theta by dt is the speed, so r times d2 theta dt squared can be written simply as dv by dt. Looking at the second part of our acceleration expression, we have got, first of all, a vector minus cos theta minus sine theta times by r d theta by dt squared. Now the magnitude of the vector minus cos theta minus sine theta is the square root of minus cos theta all squared plus minus sine theta all squared, which is just the square root of cos squared theta plus sine squared theta, which is equal to 1. So the magnitude of this second part of the acceleration is of size r d theta by dt squared. The direction of the vector minus cos theta minus sine theta is in exactly the opposite direction to the displacement. So that is back towards the centre of the circle. So this second component of the acceleration is a component of magnitude r d theta by dt squared, which can also be written as v squared over r, acting towards the centre of the circle. So there is our second component of the acceleration. That's a fairly hairy proof of the acceleration in this general case. As we said before, the important thing is to realise that there is definitely an acceleration towards the centre of the circle of size r times d theta by dt squared. So that's r times the angular velocity squared, or equivalently of size v squared over r, which is the speed squared divided by the radius. In the next two videos, we will be making use of these results to solve some problems involving circular motion.